Okay, so let's begin with the second week. 好，所以等一下我们就开始。Today we're going to talk about some more theoretical background about the large language models. Start from the very beginning of the character level language modeling, and we are talking about the BPE and word level and the BPE token level language model。所以等一下我们会从最开始跟语言模型相关的一些从 token 编码开始，然后稍后会介绍一下比较基础的语言模型的训练的相关的。再来的话，我们会再等一下我们会介绍我们这一次模组课的作业，只有一项而已，然后也是偏让大家建立一个感觉的，因为比较复杂一点训练，虽然现在来说是很重要，可是毕竟还是会需要一些 GPU 所以我们还是选择比较基础性的一个作业。And then we will announce our homework for this short course. This one will be a basic one because although fine-tuning a language model is quite essential for the skill for large language model these days, but training or fine-tuning a large language model still requires some GPUs, and so I choose a homework that is more towards the fundamental side, which is still very useful, but it doesn't require much of a GPU and can build the intuitions or feelings of the large language models. So let's begin. A lot of content and materials are taken from the Stanford's Computer Science 224N, which is natural language processing with deep learning. And some of the contents are taken from a lot of tutorials and blogs from Hugging Face. So you will find some of the slides pages are copied from the Stanford CS224M. So let's begin with character, word, and token level language models. So what are these kind of things? So before we want to process the natural languages into by transformers or even by other models like LSTM or maybe CNN or any other models, we want to encode the language, the sentence like English or Chinese or Japanese or other language like French, Spanish, into a sequence of things. And then maybe we'll encode each element in a sequence as a vector. But before that, we want to make it a sequence. So how do we make the sentence into a sequence? 所以我们为了要处理这些语言上的东西，我们会先把它变成一个数列像是数列一样，第一个、第二个、第三个才可以丢到我们模型里去。然后这个每个里头的东西可能再转成向量，编码成向量。但是我们要怎么把它变成一个 sequence 呢？一个数列呢？最简单的切法当然是我们每一个字母把它切开。然后另外上次有讲到，你可能是一个字比如说英文的话，一个标准单元是一个字一个字切。然后现在的话都是用 token 去切。那各有它的优缺点。等一下我们会先从 character 开始，然后说明 word 为什么不行，然后介绍 token 的一个演算法。那作业是会在 token 上面，在 character 上面，但是你可以选择用 token 来处理，等一下会说明。Okay, so there are three major more intuitive way to think about. The first one is using character. In English, we have 26 alphabet. If you want to do distinguish between the capital letters and lowercase, you have 22 times 2. And maybe we want some digits and some symbols. So we probably will have 100 or 200 different character. And then we can use this character to compose like word, and use this word to compose a sentence. So since every sentence can be constructed using characters, so why not we separate the sentence into characters? So that's one way to do that. And I think that's still a fairly way and quite useful way to analyze the language. And probably we will, I can still see that in future, the language model taken the byte stream. The language, consider a language sentence as a byte stream, that is considered byte by byte, instead of token by token, which becomes mainstream, because that is still workable. However, the current mainstream way to process a sentence into a sequence is split it by tokens. We will see why it is the case. And people seldom use the word level language model, and we will also talk about why we don't use word level tokens, word level language model. Okay, so let's begin with the character level model. 好，我们等一下会先从 character level 开始来解释。会有一个 notebook， 然后这个跟我们作业是相关的。For the character level model, I will use the notebook directly. There is a collab one, updated one right here, and the above one is the original one. I'll explain it with the collab one, but it is still worth reading the first one. Okay, so this is an enhancement or expansion, modified version of the first one by Peter Novick, which is quite famous. Also, it is a response. It is a modified version of the 2015 notebook, which is a response to the Capacity's 2015 blog post. Both of them are worth reading, but I'm following this notebook, and you can modify this notebook to complete your homework. 好，所以我们会照着这个 notebook 来说明 character level 的东西，然后作业就是使用这个 notebook 来使用你的资料，来使用你的资料去做东西。等一下我们会稍微从头到尾来解说一下。另外这两个都非常好的一个阅读，然后你可以从这个是原版的，2015年，这两个都2015年，这个是原版的这个东西，但是它是对于另外这一个的回应。So it is a response to this blog post, which has a title, "The Unreasonable Effectiveness of Recurrent Neural Networks." And the original notebook right here is with the title, which is hosted on NVViewer. You can download the notebook and run this as well. But I think Colab is a bit more executable and more popular. So maybe you should follow the Colab version. Okay, so the title is Unreasonable Effectiveness of Character Level Language Model. So this is response to the RNN. The Iron blog post states that by using RNN, which is specifically he's using LSTM. By using LSTM, handling by feeding and training it with like Shakespeare's writings and maybe like some source code, it can generate similar text in some amazing qualities, which like when they've training the LSTM model on Wikipedia, it will generate things similar to Wikipedia articles by using LSTM。所以这个 blog post 基本上是说用 LSTM 训练的时候，它可以生成很像你训练解东西，像是莎士比亚的作品，然后 Wikipedia 的文字，或者是像是程式码，它都可以生出有模有样的东西。One of the amazing achievement is that it can generate things like advanced mathematical article. So they generate the text first, which is a language that used for mathematics or other field like computer science publish, because it is kind of like a programming language for publishing and layout, so it can be handled by a language model. So by using LSTM training on a dataset of LaTeX source code, it can mimic the behavior and generate things like this one. So this look legit at first glance, at least at first glance. It has some very advanced mathematical formulas, looks like something real. And of course, it sort of have to be following the syntax of the grammar of the text language. So this was amazing, even today, in today's standard. But because we are familiar with large language models, so we kind of used to it. But think about it was like 10 years ago. So it was a thing. Because the article, the formula, and everything looks possible. Plus, it has to follow the correct grammar of the text syntax. So it is definitely very powerful. 所以你可以看到它有一个例子是可以生出像这种高等数学这是用algebraic geometry 代数几何算是一个比较深的数学领域。你可以看到生出来的，它用了 text 的文法去生它的原始档，然后编译成像你现在看到的这个，像是一个像论文里头的内容。然后这些数学式子有括号的，该括号的有括号这个有一点小问题你看这个括号不太对该括号有括号，然后该有箭头，该有等号。那数学式子乍看下去，你可能分不太出来它是有问题的东西，然后这些文字也都通顺。所以你看看这10年前的，他觉得这个就是 LCM 光上弄上去就非常厉害。好，那有一些生这些图，这图有点不太对了，但是大致上看起来还是 OK 的。然后还有那种 Linux source code so it also apply this on Linux source code. So that's the topics covered by this blog post. However, what is a response to what is this notebook try to explain or respond to that notebook? Is because it thinks part of the magic about the LSTM things is in the dataset or in the language model itself. Is not about the model, which we will talk about something similar in a more advanced setting, in a large language model setting. But in this blog post, the author believes that the power of what the magic of what the things we just see right here. Here is some source code generated by the LCM by RM neural network. It looks amazing, but they also believe part of the magic is because it's in the autoregressive model itself, not depends on the like neural network, but still there are something magical about the neural network。所以这篇他主要想说的是，说前面那个东西看起来很厉害，没有错，但是到底它厉害在哪个地方？有一部分其实他觉得是厉害是在这个架构本身，就是所谓的 autoregressive 自回归模型上面。有一部分把那部分扣除之后，剩下来的你可以看到神经网络厉害在什么地方。好，所以他这边就用一个去除神经网络的一个简单的语言模型来复制刚才的结果，然后看看它可以到什么程度。然后剩下来他们两个中间的差距就代表了神经网络厉害的地方。So in this blog post, in this notebook, they also respond to the LCM one and try to answer how much the neural network contributed to the magic behavior that we see in the in this blog post. And he tried to construct a simple character level language model, very simple, without neural network, and to see how much we can achieve. So the difference between this work and that work maybe indicate the contribution of the neural network. Okay, so something about the title, the unreasonable effectiveness of something. So this is a catchy and interesting title, which is originally from a book title, The Unreasonable Effectiveness of Mathematics in Nature Science, which is another book article written by a physicist, Eugene Wiener, published in this journal. So this article getting popular. It describes why we see mathematics everywhere in nature science. So because it is famous, so they use this title as a reference to contrast. Originally, this one is the first one. So this is why how this title comes from. 所以这个标题的梗就是这篇文章the Unreasonable Effectiveness of Mathematics in Nature Science， 因为这边还算蛮有名的，也被用过很多次了。但是所以那一阵子他们既然用到了，所以他这边又跟着用了一次。这篇原来主要是说数学为什么是在各种科学里头，为物理啊，还有其他地方都常常看到，而且非常有效。它就应该也都有翻成中文版或什么的。所以这是从这边过来的。好，那那篇过完之后，因为它还有蛮多回响，所以第一个它有一个 Wikipedia page， 然后再来就是你可以看到这边好几个回应。The unreasonable effectiveness of mathematics， the unreasonable effectiveness of mathematics in molecular biology and 这边这是 unreasonable effectiveness of data 这些其他是一些回应others are some response to the article, but you can see that the first three has similar titles because these titles, also this one is kind of interesting and catchy, so they are trying to use this one to describe things that has similar feeling or phenomena. Okay, so you can see that Peter Novick used this title not once but twice. This one is about the data. I haven't seen this article, and because Peter Novick always write a lot of things that's interesting. So probably I'm going to read this one as well. This one is from 2009. Okay. Okay, so let's go back to the character level things. So how do we construct this based on this? Okay, how do we construct this simple character level model? So what we do is modeling the language using a thing that calls the n-gram model. 好，所以我们接下来要用的，它一个名字啊，这招式的名称叫做 n-gram model，然后它可以扩展成，比如说你用 RNN 去做，但是我们先看比较简单的叫 n-gram model，那它可以单纯的用统计去对我们资料集做一个简单的统计，就可以来做出还不错的事情。So the n-gram model, we can use simple statistics in the training data by using simple algorithm to implement the n-gram model. So it is a generative model that estimates the probability of n token sequence. 好，所以它是一个生成模型，它主要的原理是用来估计你 n 个东西 n 个字母形成的一小串子字串啊，或者它叫 n token 啊的一个，就是只有 n 个字母所形成的一个小小的数列，它的几率用来估计它。For example, a 5-gram character model 啊，所以如果我们用5个 gram 来看的话呢，we're going to estimate the probability of the last character depends on the previous 4 characters. So for example, suppose we have 4 characters like CHAI. So what is the probability of the next character? 所以假设这个因为我们是要估计5个字母合在一起东西的一个几率，它在应用上面好，你可以直接算直接统计所有5个字母东西出现的次数，但是我们基本上要算的东西是条件几率，是这个4个字母CHAI 这4个字母，我们要预测下一个字母它出现的几率是多少。So what can be the next letters after 4 letters like this one, the CHAI? Probably like Chen, chair, maybe like other English words start or have this CHI in the middle. So for example, we can think about it. Probably it will be R or N because chair and chain are common English word. It may have like S after the chairs or like S after the or some other punctuations or like space or other later other character after this word, but we only need to estimate the next one. So it works like an auto-regression model. By given the previous things, we estimate the next one. But for the n-gram model, it is a limited autoregression model because we only consider a fixed finite length of previous history instead of consider all the previous history. So it is a simplified model. 好，所以 n-gram model 其实可以看成是一个自回归 autoregressive model， 只是说我们只考虑最后的4个字母。如果是 5-gram 我们只考虑最后的4个 character。那如果你是 6-gram 的话，你就考虑最后的5个，就是一个固定的长度的有限的最后的几个字母。So a 5-gram model is also called a model of order 4 because it maps from the 4 previous token to the next token. 其实你也可以把这个模型看成是一个像是 Markov chain 因为这种从现在的状态去 预测未来的状态这种东西是还蛮常见，在各个地方都会看到的。我们每一次只要记得现在状态，然后来想要预测下一次的状态，就连那个 reinforcement learning 都差不多是类似的概念，你都会有一个状态。那不过这边更简单了我们这边的话就是你现在的状态不一定只有现在的字母，因为我们讲现在的状态，那这个状态你可以自己去定义你的模型头可以记得的资讯。那以这边的资讯来说，记得就是我就留着你想想你在写程式嘛，你就留着现在最近的4个字母，你总会做这件事情嘛。那这就是你现在的状态，所以它可以变成一个以现在的状态去预测下一个，然后它的状态是有限多种。那有限多种，我们就可以去预测就可以去利用直接储存统计的方式去做了。So it kind of like a Markov process, Markov models. So you predict the future or predict things. The next step depends on or the next step is only depends on the current state. So what will happen at the next step is only depend on the current state. But you can define what is the current state. In this case, in the n-gram model or a model of order 4, we only remember the last 4 character. Also, this is a simple model that we can use because the combination of 4 characters is finite. We can use statistics to simply collecting the statistics of our training data. So the recurrent models or large language model can be considered as an extension of the n-gram model, but it has, in theoretically, it has more like infinite infinite tokens, consider more than n tokens, but they are also autoregressive things. 好，所以现在的 RNN 或者现在的大语言模型其实也差不多，但是它只有特别是现在 ChatGPT 这些了，那它只有考虑前面的所有字母，因为我们等一下会看，就是 n 个东西是不够的 ，finite 的东西是不够的，所以我们考虑前面所有东西，但是它还算是一个自回归模型。So let's collect some training data. In your homework, you have to collect your own training data, like 你就是你可以用去收集你自己的资料，像是你可以用中文的啦，这边就一定不会重复，因为这边是用英文的你也可以用英文的也没关系，但是你可以找你的 GitHub 的自己的程式码，或者别人不要找 Linear Source Code，因为这边有 Linear Source Code。So you can use other text like in other language other than English because all these things are taken from Shakespeare or other English texts or maybe like Wikipedia. So you can also try it on other language Wikipedia as well, or maybe other data set, or you can try on some GitHub repo, which ideally should be a large project, so you have enough data to make significant statistics. Or you can use other language text as well. So you collect your own data for your homework. So in this case, we are using Shakespeare's text here. So here's some transcript of the Shakespeare's work. And here is simple code for the collecting the statistics. It calls a language model. Because this is actually an n-gram language model. And we simply collect it used the default dict and counter to collect the statistics. So you can see that in this language model, it simply first give it a counter, an order, like order of 4, order 5, order 6, and it initializes a counter, and itself is a default dict, which means it is a dictionary. But if some key does not exist and you access to the key, it will automatically construct a default object of counter 所以它用 default dict， 然后它的物件是 counter。那这个意思只是说它很方便啦，就是它是一个你不用去每一次有一个新的 key 就去你要去 construct 它的值，你可以直接去比如说让它加等于1，让它加1这件事情。那如果这种物件本身不存在，它会自动建构一个 counter。那这个 counter 本身的话，会从一个空的 counter 开始。So by doing this one, you consider each key is the like CHAI. If you are using 5-gram or older 4 model, the key is something like CHAI, and the counter used to count the numbers of occurrence or appearance in the training data for each character. So the counter will show like N maybe 100 times or R maybe 120 times, something similar to this one. If the key is a CHAI, maybe you will also have other possibility like a space or some punctures or common or maybe some digits. But the counter store the statistics of each prefix. 所以它的资料结构很单纯，就是它会变成一个字典，一个 dictionary， 然后每一个 key 可能就是像是 CHAI 这种东西，或者其他的4个 prefix 的组合。那它的 value 呢？它的 value 就是一个 counter。那这 counter 主要记录的就是下一个出现的字母出现的次数。比如说它可能是 R 可能100次 ，N 可能是120次类似像这种情况。那可能还有其他的像逗点那些的。它这要做的就这么简单而已。而且它这边有告诉你怎么去做这件事情。So the training is quite simple as this function. For each token in the tokens, so first we will have tokens. The history we collect the token means the character or means the character. So for each character, we actually update our history. The history is keeping, if in the 5-gram model, we are keeping the last 4 characters. So using this simple update, we can keep the last 4 characters. You can also using something like DQ, DEQU, QEUE, DQ, other data type, but because usually we are keeping a rather small length of rather small size of characters, so this one is not that bad. The efficiency of this operation is not that bad. 所以这边其实你可以用比较先进的资料结构去处理它，因为这个其实有一点点讨厌的是，它加上一个 token 在后面，它把 list 变长了 ，list 变长之后又把它再截短，这个其实要拷贝好几次，有一点点不舒服，因为它首先这个加这个东西其实就有点不舒服了，因为你不是把 append 而是把它加，所以它会要新增，就是它有可能会新建一个新的物件，就要 copy 一次，然后这边的话又把它截断。然后截断倒还好啦，但是前面这边就是每次新建物件，然后截断，新建物件截断，这件事情是有一点点不舒服。那事实上，因为你的 tokens 本来就已经在那边了，你只要知道它的位置，你其实甚至不用什么资料结构，你只要把它位置，对啊，其实它可能有一些更有效的处理方式，但是因为这不长啦，而且这样写起来比较简洁，所以其实是过得去，你可以直接用它了。我不要求这边作业重新再写一遍但是我自己看到这个会有一点点不太舒服，因为这个写法 感觉让电脑很吃力哦。但是我自己有时候也会这样写，因为这样写比较简单。好，那不过总之这边就是它就记得4个字母，然后用这4个字母呢去统计下一个。你可以看到下一个是 token 嘛，然后这个 token 它就history 啊，在这个地方cat history 为什么要 cat 我不太确定它要转换它的形态吗？还是我这边没有看到 cat。等一下，对，其实我不晓得它这个 cat 是做什么用的，我看一下这边能不能找到。它是一个 utility function to concat 它只是把它 concatenate。Also, cat function is for concatenate because it is a list of things, so it is not a string, so it will concatenate things into a string. So that's why I don't think it is a good idea to write in this way. I probably will write. Okay. I definitely, if I implement it, I actually have my implementations, but never mind that. But in my implementation, in this case, I definitely will use another way to do that because this is kind of ruin the simplicity of the last one. Because if you have to write another function right here, you probably will write in another way to make this one a little bit complicated, but without this to define another function to concatenate things. But anyway, it is quite straightforward how this code means. We only collect the last 4 characters, and by using this key to collect the standard statistics of the next character。好，所以这边虽然看起来我刚才讲的我不太满意它的写法，但是这个部分其实还算是蛮清楚的，就是我们反正有最后4个字母嘛，我们把它当做 key， 然后最后一个 token 我们用 counter 去把它加1，每读到一个就加1，所以我们它的统计。So after we get the statistics, we can generate the text character by character using the statistics. So suppose we have a beginning characters, like 4 characters. So at each moment, we get the last 4 character as a key to query the language model itself, and we can find the statistics of the next characters. And we use the character. I mean, we use the probability because we count the numbers, but we use the. Of course, we need to normalize it to divide by the summation of all the occurrence of the next characters, and then we can make it a probability and generate the next character. 好，所以我们基本上得到的统计就是下一个字母、下一个 character 出现的次数。有了次数之后，我们就可以得到几率。有了几率之后，我们就用这个 random sample， 它这边也是另外一个函数了random sample 去生它下一个字就这样子而已。它做的事情就非常简单。So that's quite simple. Quite simple. As simple as what we can see here. Okay, so you can see that although I put some effort and time to explain the code itself is quite simple comparing to the large language model and all other things. Although I was saying that like the GPT or other which we call decoder-based large language models are quite simple to comprehend. But comparing to this one is still simpler because it is just like you can write something you can write in 10 minutes. 好，所以我们虽然说之前说过 GPT 很简单，但这个当然显然是更简单了，因为这个你可能10分钟，你可以想象你10分钟之内把它写完，可能写不好，可能会有些 bug， 但是这是一个很简单的一个逻辑在这边。Okay, so let's try this simple algorithm. So first of all, we try the Shakespeare's input. So for a homework, you have to use your own data set and show the generation as the following. I will you can show most of the things, but what I want you to show is only two things. First one is some samples of the original text, like this one. You should show some samples. You don't have to do things like using the head or something. You can use Python to do the similar things, but you have to show some sample to let me know, because you don't have to include all the data set in the training, but you have to show some samples in your data set. 好，所以在作业里头，你不用，你只要给我你的 notebook 就行了，然后不用给我 data set， 但是你 data set， 因为我不晓得你 data set 是什么，我也不晓得你生出来的量值是什么，所以你这边先秀一下你的 data set 原本你给我一些随机的一些 sample， 看看这个 data set 以后长什么样子。你不一定要用 head， 你可以用 Python 其实应该用 Python 比较好了，但是你要给我一些 sample， 目的是让我们知道说你这个原来的资料集大概长什么样子。详细的细节没有关系就比如说数量那些，那很重要，但是在作业里头我这边不会看，所以我只要两个很简单的事情，就是你给我你的资料集和 sample 长什么样子，然后做完这个统计去生东西之后生出来的样子。And of course, you have to show the generated text comparing to the simple one. You can do a lot of experiments like changing the order or changing the data set, or maybe you can modify the things a little bit. Like which we'll talk about how to do the sampling using using like temperature or type K. 好，你可以做一些修改，像是改 temperature 或者是改成 type K。但是不需要，就是你直接用它也可以，但是你要秀一些你生出来的样子。Another modification is instead of using character level, we will introduce token level processing, so you can modify the code into token level, because by using token level, you can see what is the magic behind the token level approach. So if you are not satisfying with n-gram approach, you can try to use BPE to making a dictionary of tokens and using token level model to generate things. It is not that difficult, but you need to use some BPE first. You can use you can call libraries to do BPE, or you can write your own algorithm as well, but you can try it with BPE. So that's some modification that is optional in this homework. But what I want to say is the original text sampling from the original data set and the things that you generated. 好，所以你可以做一些修改，在作业中你可以做一些修改，你可以用改成 BPE 可以你在 sampling 的时候可以用后面讲到 temperature 那些 type K， 但是那是选项。好，你真正要求就是你要把 sample text 弄出来，你自己的，然后它生出来的东西秀一些就行了。好，比方说这边的话，它这边用刚才的模型 random sample， 它写出了函数 random sample， 然后用 CHAI， 它就可以打出因为它只有两个东西嘛，只有 n 有78个 ，r 有35个，那它 random sample 有的时候会 n， 有时候会 r， 那这次它是 n， 可能70%不是78%，大概是113%78%的情况之下，它会出现 n；113%35%的情况下，它会出现 r。So in this case, by using a utility function random sample, and by using the statistics, we can see right here, it will sampling the next carrier in the proportion of the statistics, like about like 75%, it will be sampling like n, and above 25%, it will like sampling r. So suppose we start with THE and the space. The statistics looks like this guy. And you can, of course, the sampling utility function will sampling generate the next character according to these statistics. So let's see what is the full generation. Now this one is the full generated text from Shakespeare. I can see that looks quite like something. And if you increase the order, like this one is order 4. If you look into it, you can see that it has some strange word. So the spelling of the word is not even correct because it only has order of 4。所以你看到如果 order 4的话，乍看之下还不错，但是实际上你进去看的话，会发现它拼字有一些奇怪的东西。好 ，so you can see that it also says that it looks like sort of capture the structure of English, but the words doesn't always go together to form grammatical sentence, and there's also certainly no coherence or plot. 所以当然它刚才就是比较广，因为它只有继承前面4个嘛，就算是让你直接看前面4个字，你也没办法把那个完整的文法结构全部，因为你的记忆全部会被消掉，你只看到最后4个字，所以它能够做的事情很有限，这是必然的。这是为什么我们在大语言模型要看更远的地方，因为不看更远的地方，你在局部的结构会对，但是全部看起来会不对。So that's because you only remember 4 characters. Your memory only consists 4 characters. So that's all you see. So it is impossible for you to, it is impossible for this model to consider the global structure or like a plot or anything. So that's why we need LSTM. So at least, or like transformer, because at least in theory, it can remember a long-term history. Okay, so let's try something like order 7, which is 8-gram model. So this one seems to be much better for the words or the spelling, or maybe even with some grammar. And you can consider even longer order or longer n-gram. But with this is not longer better, because if you have longer order, it will become less creative. It will simply memorize the text. 好，所以你用越长的话，前面那个问题越少，但是它的创意就会越低，因为它有点像是背东西起来。你要是用个比如说1000 gram， 它就只能背因为他没看到的东西，他就没有资讯。那你那1000的一定是只能出现在原文里头的东西，然后它一定因为1000个你剩下的大概只有一个可能性了，所以接下来它就只会把那个东西完全背出来而已。好，你可以试试看1000 gram， 但是没有用。So you can try something like 1000 gram. It definitely will become useless because it will only memorize the full text. You only store the full training data in another format. So there's a balance between the shorter order and the long order, the creativity and the correctness. You have to choose the right order. So that's why probably the token, why we try to use token is because it's easier to balance both of them. With the help of token, you can look into a longer sequence more efficiently. 好，那这边后面做了一些叫做 probability 和什么 smoothing 这些东西，就不跟作业没有关系，后面就没有关系了。好 ，so after they talk about something like probability and smoothing, but they are not you can use the above things to finish your homework because we only need you to generate something. You choose the right order. You can just simply attempt and try different orders. Choose one that you feel more satisfied and generate your text. And probably with some optional modification like adding BPE to it or adding something like temperature. But that is not a requirement. It's just an optional choice that you can play with. Okay, so the following are other examples that you can see, and all of these examples, you should not choose the dataset appears here as your training data. You should choose other things. So you cannot use Shakespeare, you cannot use linear source code, you cannot use Wikipedia English. That's all. So that is about the homework. Okay, so this is character level models. So you can see that character level model already appears to be quite powerful. However, even if you want to make every word to have correct spelling, it will require some effort. So that makes the language model more difficult. But I still think if we get in a large and better models, it won't be a problem. 所以 character level 其实还 OK， 而且也可以做出还不错的东西，但是它会有一点点困难，因为你光是要把字拼对就不容易了，所以你要看得远的地方又会让它记太多，所以有点麻烦。就算是你改成神经网络，也是差不多的，也是有类似的麻烦。所以未来也许我们有更厉害的模型，然后它可以做到更好，那这个东西会更基本的解决这个问题。但是目前来说，我们还是用 token 为主。这边只是让大家看一下这 character level， 但是它的优点是它可以让你知道语言模型大概是长什么样子。就是 but character level model kind of like a simple model that indicate because you don't need to worry about how to do the tokenize or how to do like construct. Even with the word level, you need a dictionary. But it gives you an idea how the language model works, and you can have a really simple model like n-gram, or maybe you can try other things like LCM and compare with it. However, one of the this one is a homework description, and which we will publish it on E3 as well. As usual, you will have the time until the 1 week more after the next week. So for now on, you probably still get roughly like 2 weeks to do the homework. It won't take you much time. Probably you can finish it in like 1 or 2 hours. So that is intended. That is my intention to make this homework a bit easier for you to pass. But I strongly encourage you to try to play with it because it will give you a lot of feeling of how and why this language works like this way, and why the long-term memory is important. Also, the homework is run the character or BPE level model with your own data. 所以这边就是用 character 或者 BPE level. 其实应该是 token level, but I probably should say token level because you can use like GPT tokenizer as well. You can just simply use the GPT tokenizer to do that. But what I was thinking is because we are going to introduce BPE, so I kind of hoping you to implement your own BPE model as well on your dataset, instead of using like a pre-trained. So probably you should, because this is optional, so everything you do is kind of like extra, and because we are grading this like a pass or fail, so the actual effort will not benefit for your grading. It only will benefit yourself, not for grading. So it is your own choice. So you can do anything you wish to do, but because my intention was that you can familiar with the tokenizer, so you probably should try into training the tokenizer on your training data as well. So that's a suggestion, not the requirement. 所以我刚才说你其实也可以用 BP 用那个 GPT 的 tokenizer 直接弄就可以了，但是因为目的是要让你熟悉，因为我们等一下会讲 BP， 所以让你熟悉 BP， 你可以自己写了，但是也不用，我觉得也可以不一定要自己写，你可以用别人写好的一些 BP 套件去拿你的自己的训练集去训练它，我觉得也是可以的。好，所以但是因为就这东西是 optional 的，然后我们成绩只有 pass fail， 所以你可以自己做一个选择，都是可以的。但是要求就是刚才讲的，你要把你的 data set 的 random sample 秀出来，然后最后产生的文字也秀一下就行了。Okay, so let's talk about word level, mostly about why we don't use word level. So it works perfectly well with like the common sentence like this one. Like I like to eat apples and bananas. So each one maybe appears in a dictionary with maybe with some simple rules like S things. But we have a finite, maybe kind of huge, but not that huge dictionary. And we can simply split the sentence into different words. So if we are working with a toy dataset or doing early experiment, and we have a dictionary on our hand, it might be a viable approach. But considering the tokenizer techniques are quite common, so I don't think you should try, or you don't need to try this approach anymore. I would think. Okay, the problem with word level is it only applies to English, and only for a certain experimental research situation. Because in real world, there are many exceptions. Even for English, it may have some rare words that is not in the English dictionary. So one thing is that your dictionary may not be complete. So like in the boldface, these two characters. So this, if you are using the word level dictionary approach, these two words may be mapped to unknown, a special token called unknown. Or a lot of time we misspelling something, like this one, it should be love. Ice cream is spelled correct, but the love is LOVE, not LVOE. So this one is not in dictionary, but since we can read it and it can appear in the real data. So one way to do that is maybe you can do the spelling correction before you feed it into a language model. But that is, even if it is practical, it is not elegant. It probably is not that practical. And also we have other situations like this alternative spelling. People may write things like TXT instead of TXT, or like FRNDS like friend. And maybe it will write something like good, and it will write GOOOOD to indicate it is really, really good. And depending on how good it is, it may have a various number of O. 所以有一些这边也是状况，比方说这个，当然你普通的英文，你想象中像这样子还可以用，但是有的时候你会出现一些很少见的字，那字典就没有了。然后有一些字你会稍微拼错一点点，有一些是一些其他的拼法。And also there might be something like words that's invented recently after your dictionary has been built. There may be some new word like crypto mining. So the word level is kind of have too many exceptions. Also, English is not the only language in the world. So it may make less sense in many other languages. English or like other language, some of the other languages are similar, but they are more than just one language. So for example, in some language, I mean, of course, for a CJK, Chinese, Japanese, Korean language, the kanji and the word has a sort of different meaning, and it doesn't have as clear word splitter as English， 好像中文那些东西，它的字的分界有的时候不像英文那么清楚，所以那个本身就还需要断词，像结巴啊这种断词的东西，就第一个就很麻烦。先不说那个东西，这个反正等一下一起。但就算是不讲中文这件事情，还是有很多麻烦的地方。在很多语言中还是有很多麻烦的地方。But even if we don't consider like language like Chinese, Japanese, Korea that doesn't have a clear splitter for the word, they still have some problem in many different languages. For one thing is the language like alternative language, like Japanese, even we didn't consider about splitter, because Japanese words are like a combination of different. This means we combine different word into one word. Like it is ototo, or like a younger brother, is a combination of younger person. Also, the original native is from this kind of thing, kind of like the word's root of things, but it will have many different combinations. And also, so in some language, it will have extensive compound words, which is you can have things a word like this one. It is a combination of many different words, and there's also a thing called a polysynthetic language. So you can have a really long word like a sentence word in this language, like this one, which means he had not yet said again that he was going to hunt reindeers. So this one is considered maybe like a sentence word. And also, some language use has a really high number of inflections. So even with a single verb, like in here, the Arabic verb, it can have like dozens of forms. Kind of like English, you have the or other many other language, a word can have different forms, but sometimes the form is just too many to make a viable, plausible dictionary. So the word level approach is problematic. So sometimes, even if we want to have a dictionary, we probably want to construct the dictionary in a more automatic or more unified, elegant way to do that. So that's what we do for the token-based approach. 好，所以字典法去做，你其实问题很多啦，所以基本上我们就用 token level 的东西，你就可以想象它就是 word level， 但是这个 word 的字典是自动产生的，更一致、更自动、更演算法的方式去做这件事情，而不要局限于原本我们认为的字这件事情。我们就让演算法去决定要怎么把句子切分，更有效的一个方式去切分。好 ，So let's talk about the first tokenized method, which called the byte pair encoding (BPE). 好，所以第一个我们介绍 BPE。So this one is a popular and common way in tokenizer. Not the only one, and there are other ways that are used in more like GPT or other things. But this one is simple and easy to understand and still quite useful. So what is BPE? The byte pair encoding BPE is a tokenization method that reduces the complexity. So this is the purpose, the complexity of the text data by efficiently handling real and domain-specific words. So we are constructing a dictionary depends on the training data. So how does it do? It starts with character. So initially, we treat the text as a sequence of bytes or characters. So we begin with a dictionary. This dictionary only contains character. So here is how it works. So at the step 1, we start with the most basic form of text. It's every byte. So we start with something worse, then we gradually improve it to become better dictionary. 所以这基本上就是先求有再求好了。我们先弄一个可以工作的字典。那个之前 word level 不太，就是有时候不太 work， 因为有些字不在字典里头，太多 unknown。我们先让它能够完整编码，那先不用那么有效率。So we start with, because word level does not really work on encoding because it has a lot of unknown, possibly unknown. So we start with something that works. That is character level. So we start with the character level. That is, our dictionary contains every byte as a separate token. So it can encoding every possible text available. But we are going to improve the dictionary to make it become more efficient. Okay, so we begin with a small dictionary and we'll increase the size of dictionary. The second one, we identify the most frequently occurring pairs. So that's what the pairs in BPE. So occurring pairs of bytes in the text. We will show it step by step and how does it mean. But we're combining 2 bytes. So for at the first step, we're combining 2 bytes together to form a new word, to form a new token. And these 2 bytes, we are putting them in a dictionary. So we form a new dictionary. And we use a new dictionary to encode the new dataset again. And we observe the most frequently occurring pairs and put the most frequently occurring pairs into the dictionary and do it again and again until we are satisfied. So we can predefine a size of dictionary like 2000 or 1000. And after we reach the size limit of the dictionary, then we stop. Or we can have other stop condition. 所以基本上就是我们先找到2个最常连在一起的 token， 然后合在一起变成一个新 token， 加到字典里头去，然后我们再做一次，把那个我们所有资料用新的那个 token 的字典切割之后，找到最常见相邻的2个 token， 然后再加到新字典，一直做直到比如说我们事先定义好我们的字典要1000个字或2000个字，那就停下来。然后又或者是说你把那个切到足够的一些其他的条件，比如说你可能跟几率啊或什么东西有关的，就这样子而已。So let's see one example. This is taken from the Transformers document from Hugging Face. So let's begin with a simple dataset. We have hug appears 10 times, and the pug appears 5 times, and the pong 12 times, and so on. So at the beginning, we will have a dictionary that contains every single character. So we will split the hug into HUG and the pug into PUG, so on, PUN, BUN, and HUG. S. Now let's scan for the 2 tokens near 2 consequent tokens like HU. 所以我们这边先把它用原本的字典把它切割成 HUG、PUG 这些东西，然后再来我们要找2个相邻的那个 token. So like HU, how many times HU appears? Like here it appears 10 times HU, and here it has appeared 5 times. So the HU appears like 15 times. And also UG, let's see UG. UG here 5 times, 10 times, and 5 times, and also here 5 times. So the UG appears 20 times. And maybe we can also consider like PU, it's 5 times and 12 times, so it's totally 17 times. So we can consider each possible pairs. And we'll see that, okay, UG appears the most times. it has 20 times. So we're putting UG into a dictionary. So in a new dictionary, we are doing the splitting again. We have H, because UG is a new dictionary, we are matching it with the longest possible matchings. It has different ways to split the word. You can still split it like HUG, but because we have UG here, it becomes H and UG and P and UG and P and UN and P UN and HUGS. Okay, we do the previous process again. So here we have two tokens, H and UG. So it appears like 10 times here and 5 times here. So totally H, UG combination have 15 times appearance. It has 15 times of appearance. And also PUG appears like 5 times. PU appears in here, PU appears only 12 times, and UN appears like 16 times. Okay, so we do this in another 2 rounds, because in here probably we'll add the UN first, then we'll try to see that HUG have 15 times, then we will add HUG in a dictionary in the third step. So finally, suppose we start right there. We'll have 3 new tokens, which is UG and UN and HUG. So this is after this 3 tokens has added into the dictionary, we can encoding the original text into this new form. HUG, because it is a single token, so it has 10 times, and also here HUGS 5 times. We also have UG here and UN here. 好，所以基本上就是我们就照刚才方法逐步加嘛，因为刚才 HUG 还有 UG UN 发生最多次 ，UN 16次，然后 HUG 好像15次啊，所以我们会先加 UN 进去，然后发现 HUG 还是15次嘛，还是最多，再把它加进去，最后就会形成像这个样子。所以这就是 BPE。So that's how BPE works. Quite simple and easy. There's some consideration on how to split encoding the word, but you can try it greedily, using greedy one to make it worse as well. So the benefits for using this BPE tokenizer for large language models is that it is flexibility. It can adapt to new words or unusual terms without extensive retraining. So you can adapt to new words, because the new word maybe you don't even need new tokenizer, because even if you have a new word, it can still be encoded one way or another. It can still efficiently, if it is a combination of some existing word, then you may have already enough tokens to construct the word efficiently. But even if you don't, you still have the every single byte, so you can still construct the word as well. 好，所以你如果有新的字进去，它还是那个 tokenize 还是可以用的哦，问题不是很大。And it reduces the number of unknown tokens in the text. It actually helps the model to understand the text better. And it is also ideal to scaling across the different, diverse, and involving data sets. So that's the benefit of using tokenize. So that's why the tokenized approach, token level model, is dominated and is mentioned in the large language models today. Another method is called word piece, which is very similar to BPE. It's quite similar to, despite the name is very different from BPE. But it's actually just a BPE, modified BPE. You can consider it like a modified BPE. The only difference between world peace and the BPE is that it is not, when we choose the new token, we are not choosing the most frequently appears token. We are choosing the tokens, the pair of tokens that is going to maximize the likelihood of training data once added to the vocabulary. What does it mean? Because it means that because you know that we have 26 alphabet in English letters, but the frequency of appearance of each letter is not equal. 好 ，word peace 跟那个 BPE 非常像，差别只有在于它基本上它就差不多是一样东西啦，只是它在选取说我最常见，所谓最常见那两个 token 合在一起 token， 我要选哪一个的选法不一样，它对最常见的选法不一样，它是以几率的角度来看，而不是单纯以次数来看。原因是因为英文字母出现频率不一样。比如说好了，有些字母出现很常见，比如说 A 很常见 ，B 很常见，有些 X 跟 Y 或者 Z 就很少见。好，那如果很常见的字母，那当然就随机碰在一起的几率就很大了嘛，那它次数就很多了。可是因为那个字母本身就很常见了，你再去把那个他们，比如说 A 跟 I 这很常见，常常碰在一起的东西，那他们或者 A 跟 A 跟 T 好了，ATTA 这种都很常见，你其实不需要让它合在一起，因为它本来就是它会次数多，单纯只是因为几率上的问题，所以你不如就依照条件几率的情况来看，比方说 Z 跟 Y 比较少见对不起 ，Z 跟 X 比较少见，所以如果 Z 跟 X 碰在一起，即使它的绝对次数稍微较少，但是因为它的出现频率很高，所以如果你用 ZX 把它组成一个字，就可以有效的取代掉 Z 以及 X 的话，那这个 ZX 出现的就更应该把它加到它的那个字典里头去。So because each letter has different probability of frequency, so it is kind of unfair to only consider the number of appearance. Because suppose something like T and A are very frequently used in English. So AT and TA, the number of appearance of AT and TA should be a lot, but the number may only be contributed by simply by the probability of A and B to be high. So even if they are no significant meanings, by merely the randomness and the high probability of appearance of A and T, you will see a lot of combination of A and T. So that's kind of unfair comparing to Z, some less frequently used letters like Z or X. So if we see that XA is unusually frequently appearance, then we probably collect the tokens like XA instead of TA. But because A and T T are so much frequently appears in English, so we will see that the number of TA will be much outnumber the number of appearance of XA. But probably it makes more sense to construct a token like XA, for example, because the relative frequency of XA is higher than the relative frequency of TA, comparing to the frequency, the probability of appearance of XA, of X and the frequency of T. So we are consider the relative probability of UG relative to the probability of U and G instead of considering the absolute number of appearance of UG. So that's the only difference between word peace and BPE. 好，所以 BPE 跟 WordPress 唯一的差别就是，我们现在考虑的是，好，这个 UG 我们判断这 UG 是不是很常出现，我们不是只考虑它的绝对数字啊，出现1000次，它出现2000次，而是说，好，我们已经知道 U 发生的几率有多少了 ，G 发生的几率有多少，那以这当分母来看的时候 ，UG 出现的频率是不是出奇的高？好，比方说它出现的几率是1/10，然后 G 出现的几率是1/10。那如果随机的挑两个 UG， 照理来说它出现的几率应该是1%嘛。那如果它出现的几率，比如说已经到了30%了，那这个东西就我们用这个比例来看。哦，但是如果它出现的几率是1%啊，它也是1%，那它只要出现，因为它两个相乘的话是1/1000嘛，那它这边只要是30%，那就跟刚才那个30%是一样的意思了，因为我们只要看相对的频率，而不是看绝对的频率。So suppose the probability of the appearance of U is like 0.1%, and the probability of having G is like 0.1%. So if U and G are just near to each other by coincidence, it should have a probability like 1 in a million. So if it is significantly higher than 1 million, then we probably should consider it as a combination. So not only consider the absolute number of appearance of these two letters, but we also consider the relative frequency comparing to the single character constructing it. So that's the difference between WordPress and BPE. And of course, you can combine the absolute number and the frequency considered together and form some formula to weighted sum of these things and to construct a more useful rules to decide what combination is more frequently used. Because I think absolute number is also kind of important. It is not a only important factor, but I mean the relative frequency is also very important, and probably even more important than the absolute number of appearance. But still, if it happens a lot, then we probably should consider it. We probably should also consider about it. But this is the only difference between WordPress and the BPE. And there is also another thing called the unigram. The use of unigram is similar to our n-gram. It is to the n-gram. But uni means one. So it is a 1 gram thing. So we only consider, basically we are considering we are saying that we are considering the dictionary, that each token we're considering its probability. The goal is to use this unigram model to kind of estimate the likeliness of each sentence. So our goal is to maximize the likelihood of each sentence. We are trying to change the dictionary of tokens and use this dictionary to reconsider the probability of the sentence. We are trying to maximize the probability or likelihood of each sentence. 好，所以 unigram 是用 unigram 这个模型啊，就是 egram 的模型啊，也就是单纯的我们把句子切成那些 token 嘛，然后我们就可以算它的几率，对不对？第一个 token 出现的几率乘上第二个 token 出现的几率，就我们不管它们相连之间的关系了，我们把这个句子可以把它几率算出来。So unigram means by considering the likelihood or the probability of each sentence, we are not considering the relation between the tokens. We consider each token. We are only considering the probability of tokens separately. So that's why we call it a unigram. But we still need to has an algorithm to construct the dictionary. So the unigram start with a large number of symbols. So in contrast to the BPE or WordPiece, they start from a small dictionary. It starts with a large dictionary. And then it progressively trims down each symbols to obtain a smaller vocabulary. 所以它跟前面的 BPE 那些不一样，它一开始是一个大的字典，然后慢慢把字典变小，那让这个字典慢慢的就是依照我们那个目标然后慢慢把它就是我们希望每个句子出现的几率是够大的，然后慢慢把这个字典变小。So that's a basically unigram model. It only the name only indicate that we are discarding the relation between consequent tokens, the correlations between tokens. We are using a simplified model. So unigram actually means we simplify the model, simplify the language model to compute the probability. 所以这边 unigram 其实它在讲的是我们现在，它其实讲的是简单虽然听起来刚才整个听起来应该是有点困难，有点麻烦，不知道讲什么，但是其实它讲的事情就是我们就是要计算句子的几率但是我们太难计算了，所以我们用简单的模型去计算它，但它够好，但是它够好。Okay, so the unigram is not directly used in any models in transformers, but it is used in conjunction with sentence piece. So what is sentence piece? Then we are going to go about sentence piece later. Okay, this is sentence piece. The sentence piece is quite easy because we are not working with so in previous, like the example in BPE, we are splitting a word at the beginning. We have hug, park, or hugs, things like that. We still need to split the word, the original one. We still need to split the word. However, in sentence piece, we are considering the raw text altogether. So that's the only difference. We consider the whole text altogether. Then we can use BPE or unigram algorithm to control the vocabulary. So for people familiar with Chinese language, we probably will think, when we think about BPE, we probably will think similar to sentence piece. So, but that's the only difference. I mean, you can still apply BPE to use sentence. When I say in homework using BPE, I am more thinking about using BPE and the sentence piece together, because we are considering the whole text at once. So you can see that one of the benefits of sentence piece is it can be particularly useful for language without clear word boundaries. That means like Chinese, Japanese, Korean, CJK languages, and other language as well. Like they have compound sentence word things language that we see before. So that's sentence piece. Unigram usually work with sentence piece. Okay, so here is an explanation of how unigram works. Because we simply compute the log likelihood on each of the tokens. This is a formula. So like HUGS at the beginning. I mean, there are also other consideration, because like if we have this dictionary, BGH UG, UN, HUG. So HUGs can be tokenized in different ways, like HUGS, HUGS, and HUGS. So by the purpose or the intention of the unigram model, we are choosing the one that has the most likelihood, which has a maximal log likelihood, by using also this formula. So that's how unigram works to do the training or to do the like encoding. It always considering the likelihood depends on current dictionary. Okay, so let's begin with the large language model. To discuss large language model. So, like we start at the beginning. We use a lot of materials in the Stanford CS224 and as well as some thing from the papers, some screenshot from papers. In like 10 years ago, the mainstream approach about language model is start from the train word embedding first. So you may heard like word two factor. That's iconic and very popular one method. And we can use similar method to do things, but we start with a dictionary, and each word we have a pre-trained embedding. But now, this process has been merged into the whole training. We do not training things like training embedding first, then training the LCM or transformers. We do it in one motion. So we train the model by using kind of like auto regression things. For example, in GPT or other things like self-supervising restructuring the sentence. So not only the difference is auto regression is also almost to use to predict the next tokens. But if we are doing something like predict the middle token or correct the corrupt tokens, they are not automatically considered as in strict sense they are not auto-regressive, but they are still something similar. We can call it the self-reconstruction method. So currently we are using similar things like this one instead of like two-step or many different step things or for many small model to do the things. We use a single one big model to do the end-to-end training. So one thing that people may worry about and kind of joking or saying about the large language model is it is just a glorified auto-completion, especially like 3, 4, or 5 years ago. People may say, okay, GPT is nothing. It is not intelligent. It's just a glorified auto-completion. But after the chat GPT has getting popular, before ChatGPT appears, we already know that the large language model is the future and can do a lot of things. But I think ChatGPT is the moment that the large language models begin to appear in the public field. 所以在 ChatGPT 之前，其实那时候就有 BERT， 就有 GPT 已经很久了。那时候可能就有 GPT2、GPT3 GPT3 应该也有，因为 OpenAI 本来就有它的 Playground， 它 API 那些都可以用，然后也可以 Fine Tune 啊。那时候大家都已经知道它很厉害了，像 Instruction Fine Tuning 那些东西 ，Tuning 那些都，我记得那时候也都有玩过一些，就是用 GPT 做 in context 的 instruction，应该说 in context learning 那种东西，那时候都有了。但真正进入大众视野可能是 ChatGPT 之后，所以那个时候整个的舆论和风潮有点改变，所以大家更了解它的威力，所以也不会小看它。So before ChatGPT, because it is not in the public eye and the people doesn't aware of what the GPT is, and because you will see that and it kind of like the engram things. It just kind of like auto completion. So people kind of underestimate the power. But recently, because people have using it a lot and familiar with it, so I think the public opinion has been kind of turned to different side. But before that, people are because not many people knows that, and for the people who knows it, there are a lot of people doesn't really understand what it is, but kind of think looking it down like it is just auto completion. It's just something they know kind of how it works, but doesn't know why it actually. Nobody actually knows why it works, but because when people understand only a sum of the things, they kind of like overestimate what they know about things. So they will say, okay, it is just a glorified auto completion. But my opinion is that you probably underestimate the power of auto completion. 所以对，所以因为很多人刚开始知道的时候，他就是像是 auto regression 就没什么嘛，就是填字游戏、文字接龙，然后就因为他只知道这些嘛，他就觉得这东西其实没什么，也没办法做到什么事情。但是事实上，我觉得就是就算是 auto completion，你可能有点低估 auto completion 能够做的事情了。So the next page is we are going to see why the auto completion or things like self reconstruction things can be very useful and can force the model to learn. 所以接下来几页我们会来介绍一下，就是我们用来探讨一下为什么我们单纯使用 auto completion， 或者是让它其实它不完全是 auto complete， 因为中间也有一些填字游戏啊，那些东西，像 BERT 那些，虽然 GPT 就是文字接龙了，但是这些东西为什么可以让它学到东西 ？Okay, so we are going to list certain concepts that might be learned from this simple autocorrection or like auto-completion approach. So we'll list a few topics that a concept that it might learn from these settings. So first is contextual understanding. So understand the context in which words are used. For example, in here, she put on her high heels and something. If you want to complete this and achieve high percentage of correctness, you will have to understand what this sentence means. Because she put on her high heels and something, it should be related to her and she and the high heel. So it's unlikely to be something like went jogging because when she wear the high heels, she probably are not going to jogging unless she was trying to prove something. But it's unlikely she wear the high heels and go jogging. So it's more like something like attend a party or went out instead of went jogging. So this one is, if you really think about it, the model has to have some understanding about the word of this sentence. OK， 所以这边第一个就是你要能够对整个上下文的理解了。那像这个他穿上高跟鞋，你后面要接什么？那就不太可能去慢跑有可能是参加一个 party 或者是出去玩之类的东西。Okay, next is the syntax structure. So it can grasping the rules of language syntax, like if it runs well. So the model learns to complete this with an appropriate verb, saying like cancel or stay inside, because this is well something. So it will have become something like a verb. So it will understand the syntax structure. And also, it will have some semantic coherence. So to maintaining the meanings across sentences or within the sentence. So for example, like here, the cat chased the mouse right before it. So what does it mean by it? And what is the actually situation? We are talking about a situation that the cat is chasing the mouse, and because we are saying right before something happens. So it means it stops chasing after this action. So this action might be something like escaped or hit. So you can say that even we are trying to do the auto completion things like this one. This is definitely the next tokens. It is auto completion. We still need to have a very non-trivial understanding of the sentences in order to help to understand it. Because if you only use like n-gram things, chances are this sentence does not appear in a data set because they are practically kind of infinite, not really infinite, but they are just a huge enough number to be put into a dictionary or in the statistics files in a possible way. So we will need something to actually understand the sentence or to compress all the possible cases into finite storage. 所以这一段你必须要了解它，因为它你可以用文字接龙来说它，但不是那么容易。我们前面的 n-gram 就是我说为什么觉得 n-gram 你要去跑一下，大概去感觉它一下，你会知道这东西我有办法存下来吗？我要怎么存它？它不是很简单的说它就是文字接龙，你就是看过，然后它有相关性啊什么就结束了，因为你存不下来啊，这要怎么存？你有可以想象它怎么存下来吗？因为它的可能性有太多种了。你可以把这 cat 跟 mouse 换成别的，然后这句型稍微变换一下，它的变化型太多了。你要怎么存它？你的 n-gram 你可能想多存一点，它就爆掉了；再多存一点，它 overfitting 了。那所以你必须某种意义上来说，你要观察到，你要在众多句型里头观察到类似的句型，然后还要把它压缩成在有限的储存设备里头。就是我们的模型算很大了，但是它毕竟是有限。你不要觉得说好，我现在模型超大的，什么70B 的模型、405B 的模型，是不是甚至跟 dataset 一样大？它就是把那 dataset 背下来。就算让你把它 dataset 背下来也没有用，因为你要碰到的状况其实是有太多种了。你要把那个 dataset 你要消化整理完之后，让它可以去处理这个，其实是很不容易的事情。但是这个训练，假设说就是你让他没办法直接背下来的情况之下，你让他没办法直接背下来的情况，他可能就被迫需要去理解这个句型，然后才能够在训练的时候得到够好的分数。Okay, so another thing is like a common sense knowledge. This is sort of easier comparing to the things that we said before, but still, you can imagine that by less training routines, like training dataset or routines, it can capture the meanings of or capture some knowledges. It's possible to capture some knowledge, kind of like it will build some word model inside the language model to actually understand how the word means and how the tokens, the words are related. Also, in this example, okay, I didn't read this sentence, but okay, it also has something similar to what I was saying. It says that incorporating a general word knowledge. Also, not I probably I was going too far ahead to saying it has a word model, but at least it definitely has some word knowledge. So in this example, I went to the ocean to see the fish, turtle, seals, and something. You definitely would think this something should be something in the ocean. It could be whales or dolphins. If you were trying to talk a joke, you probably would say like a fish, turtle, seals, or plastic bottles, because kind of saying emphasis saying that the pollutions on the oceans, but it definitely was something in the oceans. In a more regular or common way to finish this sentence, because all of these things is animals living inside the ocean. So you will knowing that the most logic completion should be some kind of creature or animals living inside the oceans, like whales, dolphins, and it probably is something that you will see a lot. So it might not be something that's so rarely or difficult words. So whales and dolphins are probably the ideal choices. And also, it might have some causal relationship, knowing some causal relationship. 所以它可能可以学到一些因果关系。Because sometimes you need to understand the causal relationship in order to finish the sentence correctly. So he forgot to set his alarm, so what will happen? He was late, or he missed his bus, or he woke up late, or something like things like logically consequence of the event that he didn't set up his alarm. 所以他也可能会了解一些因果关系，因为他必须要知道才有办法好好的去完成这个句子。And also, it may have some temporal, like knowing the temporal sequence, like the order of the event. I probably should put this as a both. Okay. 所以他可以了解时间顺序的因果关系。Like after the movie, we went to dinner or home, something like this one. So it can also understand temporal sequence and may also understand something like cultural reference. Like during Thanksgiving, we usually eat, but it is something like the knowledge. Okay. So the previous things give you a rough idea, or maybe more like a high-level idea of what we are intent, or what we motivate us to train the model. 所以这边给你一个比较高阶或者是一个动机啦，说我们打算要怎么来训练模型。除了说刚才他能够学到什么之外，也可以告诉我们怎么去训练这模型。但这个东西比较像动机，那后面不，这些他能够学到的东西比较像是最后我们再分析啦，然后来了解它。那一开始可能就是因为这是一个 self-supervised 的方式，它是一个比较好训练的东西。So at the beginning, maybe we are just trying to do something like self-supervised training, because we don't have much thing to do if we don't have label data. And for language data, if we want to have like billions samples, it would be difficult to obtain fully labeled data. It might be difficult to do that. So at the beginning, I guess people are just trying to find a way to train the model using some self-supervised manner, in some supervised manner. So you can see here are some motivations. But later on, people may figure out, okay, by using this method, what sort of concept the model may learn from this procedure. So at the beginning, this is what thing that motivate us. But what is the actually concrete routine algorithm or concrete mass procedure for doing that? 好，所以接下来我们要看一下我们来做这件事情，我们是怎么真的来做这件事情。So there are different 3 types of architecture for training these things, like the encoder-based method, encoder-decoder method, and the decoder-only method. Currently, like GPT-like models are decoders method. Basically, it is just like auto-regression things. We're going to recall and review the transformer models. So you can see, have a detail about what is encoder and what is decoder. But before that, let's have an overview. So for a GPT, it is more like a decoder things, and kind of like the n-gram. we are trying to predict the next token. And this one is especially based for the generative model because we can generate the tokens one by one to predict the future world. So it is definitely like an auto-completion, glorified auto-completion, things like that. Or maybe it is not, it is definitely just the auto-completion in the heart. But there are other methods that may be interesting. So one is the encoder-decoder. So why not use it for transformer architecture if we have one? So if you can have encoder or you can have a decoder, or maybe you can have both. So why not use both? So there's some complexity. It will increase some complexity of training, but the right application for this one is probably the translation things, because you have an encoder and decoder. So like T5, T5 I think is in encoder decoder architecture for pre-training. So it one of the primary usage is for the translation, machine translation, and also there are encoders only. So which is good for to embedding a sentence into a vector. So because it is encoder, but encoder is not really suitable for like generating new text to consider as a generation model, but it is suitable for like if you want to train a classifier or other things, it will encoding a sentence for you into a representation. So models like BERT are encoder based. So let's recall the architecture of transformer. So this is the architecture of transformer. We have an encoder right here, and this one is the decoder. In each one of them, they have several transformer blocks, like we see it before. So for the input embedding, we first, of course, we need a tokenizer. I mean, for language model, we use a tokenizer to make it to become a sequence. But that is beyond the scope of transformer itself. The transformer doesn't handle the tokenization. The tokenizer does it. It's just a simple algorithm. It's nothing not too much thing about the machine learning. It's just pre-processing the data. So we use the tokenizer to make the sentence into sequence of tokens. 所以我们先把语言的句子先变成一堆 token， 然后we feed each token into a embedding. So we get the embedding of each token, and we add the positional encoding, literally adding it to the inputting embedding. The adding means the factor embedding. I mean factor addition. This is a factor addition. 所以我们先把句子每个 token 做 embedding， 然后呢，再把它加上它的位置的position 的 encoding， 把它加上去。就用向量加法真的把它加进去。你也可以 concate， 但最常见的是直接加上去。We do similar things for the decoders, but for encoders we do these things, and we pass it through multiple transformer block, like the multi-head attention, add norms, and feed forward things, and add norm, like this one that type of things. And for the output of each block, we put this result. We put an output result as an input of the decoder. So of course you because one is input encoder and the other is decoder. Of course, the output of the encoder has to fit into the decoder, so that they are pair of encoding and decoding procedure. So in here, the input are used in the multi-head attention, cross attention here. So after we do the multi-head self-attention, we do the multi-head attention right here. And we feed it to the feed-forward network and put to the softmax and the linear layer like we described in last week. Also, this is the architecture of transformer. Full architecture of transformer. Okay, so let's first see how we can train the transformer encoder separately, because the encoder can definitely work without a decoder, so that won't be a large issue. The decoder, like what we see, if we remove this part, it can also work together. So the only difference, but after if we remove this multi-head cross attention, what is the difference between an encoder and a decoder? I mean, the encoder right here and the decoder here. Because you can see that the only difference in this architecture, aside from the software and the linear part, because this one related to the loss and the output, but beside that, they are pretty much the same. They also have the input embedding, output embedding, they are the same. They also have a positional encoding, which is also the same. And the last part is feed forward and add norm, which is the same. This part, if we remove it, when we want to train the decoders alone, like GPT, we have to remove it. So this one, it won't be a problem. So the only difference is this part. And it's very small. The difference is here, in a decoder, we have a masked multi-head attention. And here, we have a multi-head attention. That's the only difference between the encoder and the decoder. So what does the mask used? So recall in the source code, we have a triangular metric. So let me first explain it in Chinese. 所以你到后面会发现，我们可以训练 encoder 和 decoder 嘛，分别来训练。那 BERT 是只有 encoder 没问题，那 GPT 是 decoder， 那本来它是会需要用到 encoder 这边嘛，就输入，但是我们把这边拔掉了嘛，所以基本上你也可以单独训练 decoder。但是如果我们把这个拔掉了，那 encoder 和 decoder 有什么差别？如果你只有 encoder part 还有 decoder part， 如果你又把这个拔掉了，那不是都差不多吗？后面这一段我们可能会加到这边做类似的事情啊，然后因为反正跟你的 loss 那些都有关系嘛，但是如果把这拔掉，两边不是差不多嘛？因为前面也是一样的嘛。虽然这边叫 output embedding、input embedding， 但就是 embedding， 然后再加上 positional encoding， 然后后面也是一样。唯一不一样就是这个 mask 的地方。The only difference is a mask part. So what is a mask? Like we recall before, we are using a lower triangular matrix as our mask in our GPT implementation, GPT2 implementation. So the mask is using to mask the future tokens. Because when we do the attention, we wish the attention to apply to only the past tokens. So we have a sentence, first token, second token, third token, and so on. So each token can only has attention to the tokens before it, not the tokens after it. So that's what the mask was doing for these models. 所以这个 mask 其实唯一作用就是让你的每个 token 只能看到前面的 token， 但是不能看到后面的 token. So the only difference between the encoder and decoder is that in the encoder, each token can see the past token and the future tokens. And the tokens before this one and the token after it. However, in the decoder model, every token can only see, if you want to generate this token, you can only see the past tokens, the token before, not the token after. So that's the only difference. And that is the reason why these models, decoder models, is more suitable for generative models, because in the context, in the scenario of generative text, we don't have the access to the future tokens because those tokens are not yet generated. Although you can imagine we are running some more energy-based models that we adjust each sentence, adjust each tokens in a sentence all at once and try to modify each tokens and to minimize the energy to find the best sentence. Not just generate one by one. You can imagine we can do that, but that is more difficult. So that's why the decoder is more suitable for generative models, because the encoder is trained in a way that it can see the future tokens. There are many different ways to fix it and use it as a generative model. It's just the decoder is more nature for the scenario for generative text. So let's see how we train the BERT model. The BERT, which is bidirectional encoder representation from transformers, is a shorthand for BERT, which is called BERT. It proposes a mask LM objective and release the weight as a pre-trained transformer. So what does it do? Okay, like this one. So this is the original sentences. We have I, maybe something I eat. I went to the park. I went to a store. I went to a store. The sentence correct answer should be something like I went into a store. But it has several ways to corrupt the original text and ask the BERT to solve this kind of like a word puzzle. So there are several different types of corruption. One is simply given a mask, something like given it to the mask. So it has a special token to indicate it is the mask, and also it will have some word that replace to a different word, which is kind of corruption, kind of given some noise, different noise. The task is ask it to find out the word, whether it is replaced or not, and to output the correct tokens for each one. So it predict like some 15% subword tokens. So not every token it has to be predict. It predicts like 15% of tokens and 80% of it. 所以它给你一句话以后，大概有15%的 token， 它叫你去猜它到底是什么。那在这15%的 token 里头，80% of the time they are masked, so you don't know what it is, and 10% of the word are randomly replaced by different tokens, and the 10% of it are unchanged. So even if it is unchanged, you don't know which one it is unchanged. It could be something like I pizza, and this one is choosing another, but we know that it is grammatically incorrect, so this must be something we have to be, some tokens has been replaced. But also note that it's worked on a token level, not in a word level. But to demonstrate this example, it is easier to show it word by word. So for the rest of the examples, you probably will, because we recognize the word, not the tokens. So you should translate in your mind that each one is a token instead of a word. Okay, so one of the limitation of this transformer encoder or this pre-trained encoder is that it is not very good for generating things. Consider you are using a decoder. It is because you are predicting the next one. So you just put the next one as input and predict the third one and predict the next one and the next one and the next one and the next one. So it's very natural. Like we said, the decoder is very nature for doing generative tasking. However, for the encoder, it's most likely you to just need the so if you want to simulate the same thing, we probably have to do something like if we have the first three tokens, we probably will have something like mask, like mask, and ask it to predict the next one. And after we have the next one, we got the first. One way to do that is we predict the last three one and mark them as mask altogether and predict it at once. But it may not be generate that good things because it is a very difficult task and you have to do this in one run. And the decoder has the chance to do it in multiple runs. So it makes it even more difficult. And another approach might be, okay, we put all three to be masked, but we predict it one by one. In this case, it will have more computational, consuming more computational power. And it may not be that easier to do that because the model doesn't, in the training, it doesn't see that many masks in the training data set. So for this case, if we want to start from the first tokens to go on, we will have like 1, 2, 3, 4, 5 masks. And we don't even know how long it will go. So it is doable, but you can try to find some algorithm to make it to generate text, but it is not that it is not designed to do that things. So that's why people use GPT approach, like auto-regressive approach, it is more popular in today's generative AI models. So another way is to train the encoder and decoders together. There are many different ways to do that. So the way that to train the model T5, which you can see in a lot of T5 is still used in a lot of different places and has a lot of different variants. So it is mostly using it for, the original purpose is for using it for the translation in multiple language. So the one way they do is that they still do some corruption to the text. It gives you something like, thank you. This one is a special token for the first part. Me to your party. This is something right here. And you have to answer something like X is equal to for inviting and Y is last, or things like this one. So this is how they train the T5 things. The difference, there's some subtle difference between this one and the previous one is this can be multiple tokens, not just only one token. It is not just a mask. It can be multiple tokens. So it's more suitable for you need a decoder to that. You cannot do this with encoder alone because it has multiple tokens. So it can do some generative things. And so that's a main difference. Okay, so another way to do that is for Okay, let me see the time. Okay. Another way to do that is like GPT to pre-train the decoder. So this one is pretty straightforward. We simply do the auto regression things. So each time we give the first few words and we want to predict the next ones, you can do this bunch of, because we have a mask on things, we can do this in one run. Like using W1 to predict W2, and W1, W2 to predict W3, W1, W2, W3 to predict W4. Because we have the mask, we can train this sentence in one run. So this is pretty much the pre-training for decoders, which is kind of easier than the BERT one or maybe in the T5 one. So this one is like the GPT pre-train method. There's one paper that published by OpenAI to call the scaling laws for neural language models. It is one of the milestone paper to give us information of, or give us some evidence that how the large language training works and why this approach might have a future. By their observations, this paper is published in, I think is in 2020。所以这篇是 Scaling Laws for Neural Language Model 是2020年的一篇 paper， 在 OpenAI 出版的。那这篇 paper 它某种意义上就告诉我们说，为什么大模型是好的，而且越大越好，越大越好。然后它探讨了像是几种，主要是这三个东西的关系。一个是叫做compute 计算的量，一个是你的 dataset 的大小，你有多少 dataset 的大小，另外一个是你的模型的 parameters。那重点就是 parameters 这三个东西差不多就是最关键的重点，而且三个都要变大。那模型的架构本身影响不是那么大，然后他们都符合了一个 power law， 也就是说这边我们某一个次方啊，你把它看上去之后，它会像一条直线啊，它的上限或者它的预测未来的，比如说它那个 loss 下降的趋势会像是一条直线。So in this paper, it discussed and studied the relation between the three primary effects that can be related to the result of the large language models. The three factors are compute, the computer powers like how many days of computations, and the data size, dataset size, and the parameters in the model. So the size of the model. So these are the three major factors that affect the result of the language model. Other factors like the architecture of the models is not the primary factor. They have some effect, but not the major one. They are minor. They are the minor factors. So the key point is language models performance improve smoothly, as we can see that like kind of like a straight line. When we increase the model size, data size, and the amount of compute used for training, all these three has to be increased in a relation, or they are given a relation, like they are related by some simple rules, like a power laws relationship, like 5.4 times like 10 to 13. So this, you have the data size have to follow these rules, and the computer have to follow this rule, these power rules, and the n indicate the parameters has to follow these rules. If they are increased follow these power rules, then the performance is going to be guaranteed. At least in the scale they observed, the empirical performance is a power law, has a power law relationship, and all these three, if increased accordingly, the result is predictable, kind of predictable. But if you only if some parameter is left behind, it will become the bottleneck. So the optimal relationship between all these three things, they figure out power laws between them to have the best performance. So this is worth reading, and it summarizes certain rules they observe. 所以这边你们可以去看一下，它有把最主要就是刚才那3个东西啦，就是它必须都要增加。那其中一个如果增加不够的话，就会变成 bottleneck 啊，这是他们观察到的现象，是这样子。So the parameters depending. So the following are several rules, several summaries that they provided. Details are provided in the papers. Okay, so let's walk through some of the summaries they observed in the paper. The first one is the performance depends strongly on scale, weakly on model shapes. 好，所以第一个要点是模型的表现主要会被影响到的是它的 scale， 就刚才讲的那个 NDC 啊 ，N 是代表的是那个parameter model parameters，D 代表 data set 的大小 ，C 代表 compute 的 training。It strongly depends on these three different factors: the model size, the size of data set, and the amount of compute for training. But only weakly, only minorly depends on the model shape. Like, okay, people may argue like the more deep, the better the model, or maybe we should have a shallower model but wider, or maybe they have the sweet part of the ratio between the depth and the width, maybe, but it's the study empirical experience result indicate that this effect might be minor. So you can see in this paper in detailed discussion, but the conclusion is that the major factor is the scale, not the model architecture or shape. Okay, the second observation 第二个观察这边有一个小结论是it calls the universality of overfitting. It says that the performance improve is predictably as long as we scale up both N and D in tandem. 就是我们把 N 和 D 同时变高。你在训练的时候可以 compute 你可以一直下去，但是它可以就是我们这个如果 N 和 D 都已经够大的时候，然后这个 performance 它的是可以预测的。But if one of the N and the D is fixed, then the return is diminished. So you have to increase N and D together in using their rule. So the rule is the power law is the ratio of N power to 0.74 and D, the ratio between them should be fixed. So meaning every time we increase the model size 8 times, we need to increase the data size roughly by 5 times to avoid the penalty. So that's the ratio between the model size and the data set size. So that's their rules. the power law for the ratios between the dataset and the model size to ensure the performance of the model. So the other rule is that the universality of training. So the training curve also follows a predictable power law. The parameters are roughly independent to the model size. So no matter what is the model size, the training curve is kind of like the following the power law. The parameter means the scale, the constant scale of the power law. So you can actually predict what you can achieve if you train the models longer, because it generally follows the rules above. So that's the universality of training. Here. Here is also another rules that is quite interesting, that when it works with a fixed compute budget. So this is more kind of toward the practical side. Say that if we have a budget, like $1 million, $1 million Taiwanese dollars, or $1 million US dollars, and you want to train a model, then without any other restriction on the model size or available data D, they can obtain the optimal performance by training a very large model. So if you have a limited budget, if the budget is limited, then it is preferable to have a larger model and stopping it in a short time. So it will be cheaper to training a large model than a short training time, than comparing to a smaller model with a longer training time. Because like it says before, the training performance will getting better if you put more computation inside it. But if you're training longer, the performance is getting better, like the universality of training says. And at the range they were experimenting, the performance gaining is predictable. However, if you are having a budget, if you're having a budget restriction, you can use their formula and their experiment result to decide how much budget. You can calculate the cost of each possible configurations, and they find out that if you have for a given budget, it is usually cheaper to training a larger models than a small model, because large models converge fast at the beginning. If you're considering the performance. OK， 所以他这边基本上就是说，如果你的预算有限，在他们实验来说的话，如果你的预算是有限，至少在他们的情况之下，预算是有限的话，你用大模型因为大模型它下降比较快嘛，然后虽然它的 C 越大，它就会下降越多，前面说的但是就是你的训练越久，它下降越多，而且是可以预测的。但是大模型它一开始下降比较快虽然它后面还有更多潜力可能可以下降，但你停比较早，你可以比较早的停下来，这时候可以得到更好的结果。所以他这边大致上给出一个结论，就是我们的那个 computation 的cost 和那个 data size data 的大小他给你一个 rule 去做它。好那它there are more conclusions like also like a batch size. What is the optimal batch size? consideration of other things as before. But I only pick a few of them to demonstrate right here. Okay, so after the model getting so we still have many materials, but I probably will start with the in-context learning things and put all other things like the fine-tuning things in next week. So the last topic about this in this lecture is about in-context learning. 好，所以我们最后再讲一下 in-context learning， 好，就是我们今天最后的一个主题。So after we have a very large language models, it kind of seems to perform some kind of learning that without gradient steps, by simply given examples you provide within their context. This is from the original paper. It says something similar thing like that. So GPT-3 is a canonical example of this. The largest T5 model have 11 billion parameters, but the GPT-3 has 175 billion parameters. So it is something that you heard about the emergence of the large language model. So when the large language model kind of passing through some threshold of parameters, it kind of showing something intelligence after the model is large enough. There are some control argument about these things and some evidence showing that the emergence of the large language model is just an illusion, but this is what happens before people think like, okay, GPT-3 is getting a quite large, and it kind of showing something surprising and kind of intelligence, which we will show you in the next slide. That is the in-context learning. 所以in-context learning 其实可以有两种方法来说，一个就是它是一种训练，它可以看成是一种训练，但是不是你常常看到的那种 gradient 的那种训练，而是看起来像 few shot 啦，就是你直接给它一个简单的几个例子，它就可以执行各式各样不同的任务。那这个有个可能就是神经网络或大语言模型的爆发，可能听过这个词，就是它突然智慧突然 emerge 突然爆发出来啊。那就是 GPT-3 是第一个这种典型例子，因为它模型真的很大，以当时来说啦，它是真的相当大的一个模型。那它有展现这种看起来不知从何而来的智慧的现象，所以有这种说法但是后来有一些人有持反对意见。那不过这就看这不是很重要，就是它不影响你的其他事情所以你就把它先当成是一个存而不论，就是有这种有此一说，我把它当成有此一说，可以来看一下。好，那 let's see the example. The typical example is this one. Given some input, because the model has already been trained on the French text and the English, it cannot automatically learn the French by 3 examples to construct a whole French language. It cannot do that. It has the knowledge inside, but it hasn't been training with something like this one, like the examples, like thanks can train to mercy, hello training to bonjour, and mint train to manze. And if you give this example, even though if this kind of thing is not exist in the training data, because in the training data it might be something like Wikipedia or article things, but even though it doesn't have these things in training data, if you give this example like this one, it will figure out what you mean. So it will output the these things in GPT. It will output things like this one in the corresponding French syntax. You can try it in OpenAI playground using an older model like GPT-3. You should not use the chat model like instruct tuning models like ChatGPT. You just use the original pre-trained GPT model, or maybe you can try like the Llama pre-trained, Llama pre-trained, not instruction fine-tuned model. Like if you try to find the Llama model, you can find something like chat fine-tuned or instruction fine-tuned. Do not use that. If you want to observe this phenomena, use the pre-trained model only. And even that model doesn't pre-train on the dataset with format like this one. If you don't believe that, you can change the format to other kind of things, like put this in like emoticon, or maybe like I don't know. I haven't tried it. I have tried it for emoticon, but I haven't tried it like you know, people may encode the word like Chinese word or English word into numbers. In English, like LEET, L-E-E-T, you might want to translate it into digits like 1337, because it kind of look like LEET. And in Chinese, of course, we use the 在中文的话就是你可以试试看别的形式，不一定要用这种中文翻别的语言，或者是说我们之前用那个表情符号。我刚才讲说表情符号了，那你可以试试看，比如说翻成数字就什么一生一世嘛，就1314，类似像这样的，看它能不能自动帮你找出它的那个数字来表示它的那个文字的方式。你可以找一个它可能不在资料集里头，然后去试试看。你可以找那个你要用的模型，不要用那个已经被什么 chat fine tuning 或者 instruction fine tuning 过的东西，不要用这种东西，你就用原始那种 pre-trained model， 因为它的资料集头没有这样子，你就可以观察到这个所谓的它在没有训练过的情况之下，它还是可以做出这种简单的类比推论的这种现象。去观察到这个当年大家发现的这个奇迹。有两个地方可以试一个就是你用 API 找一个早期一点的模型，或者是用 local 自己架，就像刚才找的，就是 Hugging Face 找一个比较早一点的模型。一些早期类 GPT-3 模型，或者是像现在拉玛，但是你用的是 pre-train 的那个，不要用到 fine tune 的那个。所以这是一个还蛮有趣的现象。So other more okay, we haven't talked about decoding and other things yet. So other similar things, I probably should put it later, but I put it here. So let's be the last part. So another thing is similar to kind of sort of demonstrating the AI, a large might have some intelligence. I won't use the word like mind or like perceptions or it is essential beings or like that, but it can demonstrate certain level of intelligence, is that which we call the chain of thought prompting. This is all so for this is one of the early example of prompt engineering, and the chain of thought has been used in a more wide range, but the original, I think it is the original one, it is called the chain of thought prompting. So what it does is something like this one. If you ask a question in early chat models, so this one is for chat models, not for the pre-trained models, but for something that requires some reasoning, like this. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So it gives an example right here. The answer is 11. And here's another question. So this is also example based, but I believe this one is working on ChatGPT, not the pre-trained one. But this one is still in the realm of in context learning. But in here, because we give one example and we give another question and hope it to answer the correct answer. So here, the cafeteria have 23 apples. If they use 20 to make lunch and brought 6 more, how many apples do they have? So it requires some calculation and reasoning. And currently, it doesn't have a correct answer. However, by a simple trick to give an example and ask it to do it in steps for here, not only we instruct it to give some the answer only, it show it step by step. So because of the in-context learning, it will do the same. It will follow the same pattern of the example. So it will answer it step by step. And the observation suggests that if we use this pattern, the chain of thought prompting pattern, it will have higher accuracy of answer the questions correctly. 好，所以这个就是原始的 chain of thought， 就是它用给例子的方式。例子不是只给答案，而是例子有包含了就是步骤。那只要给上步骤，更完整的范例，教学的时候更完整的给出范例，而不是只给答案，那他就会照着这个来做，因为他是in context learning，他照着来做嘛，然后他就会给出更容易给出正确答案。好，所以这是其中的一个。当然现在这边是一些其他例子。So these are some other examples of chain of thought. I from the original paper, I put it right here to let you have an idea of what it does. So it can, if it output longer generated answer, it will have a higher accuracy of correctness. Okay, so this, but in recent years, sometimes we simply, because the models are instruction fine-tuned, so we simply give instruction. So, okay, you solve this step by step. We don't even have to give it examples. We just give it instruction to give us result step by step. That alone can also improve the simple prompt tricking can improve the accuracy of correctness. Okay, so that's all about today's topic. So next week we'll continue to do the decoding process, the certain more advanced training method like instruction fine-tuning or reinforced learning of human feedback, things like and some other more advanced training techniques. Okay, so that's all for today's material.